been around vertical labs for the last few years, dealing with IPFS, Filecoin, things like that. Before that, academia, studying distributed systems and doing a set of access, so like censorship circumvention network protocols, and sort of looking at that space of internet infrastructure and the network layer. And this is just sort of a set of reflections on where things are, what building blocks exist, and how to think about what that space of privacy looks like at the communication level and outside of the distributed system. So you've got some set of properties that you can do in your computation on your nodes, but you've also got a bunch of communication that's happening. And a lot of the protocols that have come out of a crypto space, at least, are not spending a lot of time thinking about how they structure that network layer, right? So we've got a few things that get pointed to. I think NIM is maybe one example that's looking at network level privacy. But in general, there's a lot of systems where you look at it and you're like, oh, but just the communication patterns that are happening around this are already going to be leaking a lot, and we need to be thinking about that as part of an overall set of guarantees that you're trying to make about some protocol or some system. There's an interesting trade-off that a lot of this can get framed within. There's many of these triangles. This one is that you're going to end up in a tension between what sort of anonymity you've got and sort of an efficiency/latency thing. You're either going to be sending a lot of additional traffic that you're hiding within, or you're going to have to wait a while for other people to be doing things or for other things to happen that you're blending with. And so there's this conceptual trade-off of like, what is the set that you're blending into? That's one of the sort of initial things to be thinking about in terms of how you structure this conversation about anonymity. We've got a set of building blocks that are probably the first ones that you come to, are the ones that have gotten a lot of attention and hype. So zero-knowledge proofs, homomorphic encryption, multi-party computation are building blocks that we use to talk about how we're going to protect communication, or about computation. So you've got some circuit, you've got some thing that you're doing at a node, and you have a system that you can build around it to limit what gets exposed about that computation or protect it. But you also need to be thinking about the graphs and the patterns that can come out of it. When you talk about the adversary or the threat model, the one that's probably most well-defined is to talk about a global passive adversary. That's an entity sort of like the hypothetical NSA-ish actor that can tap into and get records of a set of its choosing to some extent of edges of communication lines. So it's not limited to a single country or geography. It probably can, as an adversary that's state-funded, get access to some communication lines around the world. So when you talk about what is the privacy that you're trying to do, what are the properties, we've got end-to-end encryption as sort of and transport layer encryption. These terms refer to the content of message that you put it within an encryption envelope, and now you can't see what the specific contents are said. And so the metadata around that, there's a few that are probably the most relevant when you're talking about sort of the next steps or what you need to be thinking about in these systems. A big one is the communication graph of who's talking to whom. If you can link a from and a to and say Alice sent the message to Bob, that already is starting to let you derive social networks, social graphs, a bunch of communication things, or a bunch of who are users of Tornado Cash, where did values flow through, even in a set of blockchain protocols where the actual financial amounts are hidden or masked. If you can follow the path of transactions of messages are being sent from account A to account B, you can end up learning a lot about what financial flows through. The other ones are probably the sizing of messages, if that's meaningful at all. So if messages, a long essay may be different, or a picture will be a lot more bytes than just a text message. So what can you learn about the sizing, and are there ways to protect that? And then the timing and sort of the, okay, there's messages from Al to Bob, followed by back to Bob to Alice. If you can start to get these ping pongs, even with some amount of limiting, you can start to find conversations versus one-off types of things. You can see patterns and distinguish applications. So lots of things, lots of potential pitfalls, lots of, I don't know, a space where it's hard to say this is private or this is anonymous. And so the next thing in terms of structuring or approaching that is what metrics do you use? What do you use to say something is private or more private? There's sort of three constructions that get used most commonly. The first is k-anonymity. So you want to talk about the anonymity set that you've created. So if I'm able to mask the communication between Alice and Bob, how many other recipients could a message have? How large of that set? So that gets used to quantify, okay, this is more private, there's a larger set that I'm hiding with it. There's a concept of linkability. So I want to, as an adversary, make a guess of identification of a message. And you can start to say, how much better than a random coin flip does the adversary have of being able to make that guess? And so now you've got sort of a numeric statistical thing that you can rank on of, okay, it's 1% chance that above randomness, that, or it would take so much information for the adversary to start to be able to make these inferences correctly. So the remaining power to an adversary to be able to correctly identify things is a quantitative metric that you can use to try and talk about relative levels of privacy. And then there's a third one. You can break this down a little bit depending on constructions. There's things that will try and de-link just one party or de-link just one part of a process. So you can have more specific concepts like this general concept of linkability. The third way that people measure privacy is a metric of indistinguishability. This comes out of differential privacy ones and is more for data sets. And so in this one, you talk about sort of the statistical distribution of your data, and you look at how perturbed individual items are. So how distinguishable is a given message from your data set? How much would it need to change to blend in with other items? And in doing that sort of statistical movement, you can create a metric of, okay, all of my stuff just fits the normal distribution very closely, and so this, as some element in that normal distribution, does not reveal more information than the distribution, and it becomes not by itself a meaningful thing for an adversary. And that one's more data set versus like the communication network. So depending on the type of system you're building, different ones of these are going to be more effective or are going to be the thing you reach for. Okay. So that's sort of context landscape, how we talk about it, what the adversary, what the framing is. There's a few different primitives that are, I guess, most relevant in dealing with network privacy. We've got a set of things around statistical masking of communication patterns that get used both by mixnets as well as by systems that are just sort of trying to make it harder to observe their traffic. So even if you don't go through multiple hops, you can delay messages or send messages at a given pattern in order to make the communication pattern that's actually happening harder to understand. There's a whole set of things around how you might pad messages to quantize them, to have less information about the actual sizes of things of communication and hide that piece of metadata. And then you've got a set of things around dynamic cryptographer as an individual primitive along with multi-party computation that is sort of a direct approach to get into a k-anonymity space. So if you can have a group of a known size come together and do a cryptographic process such that a message can get generated jointly where none of the participants can know which individual participant from that group was the actual originator of the messages or receiver. And then there's a construction around private information retrieval, which is a problem for how you pull an item from a database without revealing which item is being accessed to the server that holds the database. And there's an academic set of things going on in that space that some use homomorphic encryption, some use in information theoretic construction. I'll talk a little bit about what's new there. Okay, statistical communication. This has been around for quite a while. Like in the 80s, 90s, we had some very early email mixnets that got created. Mixmaster, things like this, that basically say we'll have a set of 3 servers, and the server will wait for 10 messages to get sent. It'll shuffle them in a different order and send them to the second one, which will shuffle them into some order, send them to the third, which shuffles them and sends them to the destinations. And if any one of those 3 servers properly shuffles, then no one else really knows this ordering, and you've got an indistinguishability between the 10 messages that got waited. So you've got this constant size that gives you a known k-anonymity. We're going to wait for a batch of 10 messages. We're going to sort of reorder them, remove the froms, and by the end of this process, there's not a passive adversary, and none of the individual servers, if they're malicious, know how to link the senders with the messages. The problem with that is now you're waiting an unknown amount of time for 10 messages to show up. And so, especially in a not super well-used network, you're like, well, is 10 enough? What happens if the other guy sends 9 messages right after mine? Now it's pretty clear which one was mine if that adversary knows about the other 10. So there's a set of things that you get a little concerned about. And so both for predictable performance reasons and for some of these, civil issues of an adversary being able to spam, a lot of things have moved towards more statistical constructions for this. And so with that, I will hold your message for some amount of time, and I will decide that amount of time as an exponential decay typically, where I sample from some distribution and say, okay, for this one it's going to be 1 second, for this one it's going to be 2 seconds. I'll be mostly holding them for some amount of time that I've got based on some global property that I calculate every once in a while about how much is flowing through, such that there's time for things to mix. And it becomes hard to look at the stuff coming out and directly correlate it to what's going on. Okay, so this like concept of how long you're going to hold on to things and how much delay, how much latency you're adding in order to build up this anonymity set is something that's been dealt with by a few different systems. There was a system a decade ago called Pond by Adam Langley. It was done a number of things that were just a direct messaging client server that was trying to be how do you make a really strong anonymous client server. And it was one of the ones that sort of prototype having this set of, okay, we'll do this exponential decay. And here was the README description of what they felt like they got out of doing this additional latency introduction. So the connections are randomly timed rather than some constant period, and that avoids the server learning when users are sending messages. Because you've got a historyless thing where you don't say, I'm going to send my message to my server every minute, but rather you do it with this decay fall-off where when your laptop goes offline or you lose power, the server can't tell if you just hit, unluckily, a really long delay or if you've actually gone offline. And so you get this property through that decay that you are able to some extent, hide what your actual uptime or your actual activity with the server is and de-link that from your communication pattern. So there's a set of these statistical things that that give us this property that gets called memorylessness, where the fact that I've already waited an hour, I can't predict was that unlucky versus am I going to still wait another hour, that the slope of the remaining distribution is the same. So this is as good as anything. If you have this correlation over time, there's still stuff you can pull out, right? If I can see, even though you're sending this, that you never send messages for 8 hours in the night every day, I can eventually figure out what time's that occur. Things like that, right? I can't tell it at a given time if you are offline with full knowledge, but over time I can still build a statistical guess of when you're more active and when you aren't. So this isn't a full protection, but it limits the knowledge. Figuring out how much it limits the knowledge gets a lot harder, right? How long does the server need to be collecting the communication patterns to understand, okay, like I'm seeing regular communication through these hours, I'm never seeing it on these, I bet you're a mobile device in this time zone. There's not a great like model where you could say, okay, that it's going to take n messages before you get 95% confidence, but just intuitively, weeks to months of that sort of pattern of something that's used with any frequency, and you can probably pull out and observe that stuff. So unless you've got that parameter turned really conservatively, you're going to, relative to these periods of activity, you're not fully detecting stuff. Or you just have to leave your phone on all the time, right? There's a couple options. Okay, padding. So how do you hide the fact that this is a picture versus this is text? Most things don't, I guess is the high-level answer. So if you look at Signal or most of the messaging we use, they use different systems for text and for attachments. So like if you're using Telegram or Signal, your images and movies are just getting uploaded to an AWS bucket or equivalent, whereas your actual text messages are getting sent with a different encryption set of primitives and going through a main routing server. So you, in general, the security of large amounts of content is getting deferred because it's too expensive. There's been a set of work around web browsing. So I'm visiting a website, and can my ISP or can someone in the network look at how big the response was and say that was Google because it was small, and that one over there looks more like YouTube because it's much larger. And in particular, most websites have different amounts of resources and are not exactly the same amount of bytes. And so even though you've got TLS and encryption, it's actually not so hard to be able to fingerprint specific web pages that people are going to just from the size of the responses. And that's a little scary and unfortunate. And you're like, okay, I use a VPN, but still, with a VPN, like, unless you've got some amount of padding, it's the same length of Google, right? The Google page HTML is not like wildly changing. It's roughly the same amount of bytes. And so that's gone through another layer of a symmetric block cipher. It's different. You can't unencrypt it, but you can just look at, okay, there was a query, like an outbound packet went with 250 to 300 bytes. That's probably an HTTP GET request, and something came back that was like 3K, and that's roughly the size of Google's homepage. So there's been some work on like how much might you want to quantize and pad things so that there's big blocks of websites that all come together. There's a couple options that have different levels of this trade-off between how many extra bytes are you willing to pump through your system versus how well can you group things and quantize them into these are all looking the same. The easiest one is you say, when I send a packet, which typically has an MTU or a transmission unit size of 1.5K, I should just always send a full packet. I shouldn't do half packets or whatever. So I'm either going to send the packet, pad it out so that it is all 1,500 bytes, or I'm not going to send it at all, and now I've got a quantization that's full packet length, and I've at least limited some of those individual things, and I haven't really hurt myself. That's not really an overhead. I'm sending the packet either way. The client device is going to have to parse the packet either way. The fact that it's got some extra zeros at the end, once it decrypts it, isn't hurting very much. That alone isn't, unfortunately, solving a huge amount. There's still a bunch of website fingerprinting that's possible. The ones that have been shown to be effective is, you say, if I'm going to be sending stuff, I will just spam traffic as much as I can for a second. So I'm either sending for this second or I am not sending for this second. That turns out to be pretty effective and gives you very large buckets, but at the expense of you sending a lot of cover traffic. I help with the Tor exit node based in the US. One of the things we've done is we have an edge to our network that's in Europe. And so all the traffic coming to us in Europe enters our backhaul network in Europe. And we have a constant bitrate pipe between our edge in Europe and in the US. And so the traffic that is going over the undersea cable that is most likely to be watched by an adversary is just going and saying bytes all the time at the same rate, regardless of what messages are actually going over it. And we think that is somewhat effective at making someone who is watching sizes of traffic and bursts of traffic not be able to see much. But it's very hard to know how effective, because it's against a passive adversary who does not reveal anything. So we have some sense of theory of like, if there is someone trying to watch this link, we have made that much harder. But we are in an iterated game where there is a very slow feedback loop. Okay, so that was padding. DC nets. So Dyne cryptographer is a cryptographic primitive, came out of Chom in the late 80s, where you've got a group of cryptographers who want to do something like communicate a sum or get some bit of does anyone raise their hand without knowing which one did that. And so there's a protocol that you can come up with that gets that. And that has gotten used by a set of systems for group communication. So you can have messages generated by some subgroup and then broadcast. So often this gets used for like publication, where you can't tell who is writing a message on a bulletin board. It could be any of the group members who has posted the message, because all of them essentially perform this Dyne cryptographer dance to get there. You're able to get to order of 100-ish sized participants in a DC net before your communication costs and the time that you're spending to do that gets completely ridiculous. But you're still, like, once you're in hundreds up to maybe 1,000 or so nodes, you're looking at order of minutes to generate one message. But you've got this reasonably nice thing of those users are online and you can't go below the group. And so that, along with things like an end-to-end encryption, means you can still overlay on your one-to-one communication or whatever other process while still knowing you've got a can nobody said. The real trick in using constructions like this is lifetimes of users and user churn in a real system, which is if you stay with a fixed set of 100 nodes that you're going to be your anonymity set and all of your messages go there, great, you got 100. If it's find the next group of 100 every time you send a message, then over time, by looking at those group overlaps, you'll end up being able to narrow down the sources of messages. Okay. There's Descent, there was Ripple, there's been a set of stuff, a lot of it from this Dennis group at Yale most recently, and then I think Brian Ford is now in France or Switzerland. So there's a couple academic groups that are trying to look at construction around this. Private information retrieval. Okay, so this is the basic stating of the problem. I want to get some item out of a database without the server knowing which item I've gotten. The straw man for helping feel confident that this is possible is I can download the whole database and then locally grab the one item I care about, right? Like, the server has not learned which item I cared about. It's just extremely inefficient. And so now we need to make it more efficient. So there are two main branches here. Information theoretic, you make your problem easier by saying you have multiple servers that won't collude. So you go into something that looks sort of like an MPC-ish or threshold network, and that threshold assumption gives you a place to do this. It ends up being very easy in terms of like your computation and math, and people are showing that this works for pretty reasonable, like the sizes of things that we are dealing with. So 2 years ago, Spiral PIR got balances of all Bitcoin and Ethereum addresses, and periodically updates that. I think they update it every hour or so, but you can query any balance without revealing which balance you're querying. And they're able to do that pretty efficiently. And so you could imagine, okay, if they can do that and they can do that efficiently, that seems like something I might want in a Brave wallet or a MetaMask. Like, I don't want to like have the RPC provider know which account is mine that my wallet keeps querying. The other one is homomorphic encryption based, so FHE type things. These also are getting there. They're a little bit higher computation for the server, but at the benefit that you've got a single server that you're talking to. So you've got an easier scale thing. You don't have to deal with online. You don't have to deal with synchronization of updates. So I mentioned Spiral. That's now upgraded to the list, but their code's open source in Rust. There's a set of work going on around authentication or handling malicious servers. You end up with a 10 to 100x performance hit if you want to know that the data item you're getting back from the server is the right item. If you've got signed items in your database, you don't need to do this. Like if it's a message from some other end user that's ended encrypted and you can verify that they sent it, great. But if you have no authority, if it's just the balances that aren't necessarily signed, or you don't want to download the whole transaction history to get there, and so you're making sure you don't get lied to, you need to do something to make sure the system is somehow coherent. There's a set of things that a lot of where people are looking right now is this intersection of how much churn your database has, so how quickly you're getting updates that you need to be able to push through that pipeline versus your reload. So if you've got a lot of queries in a relatively stable database, you can pre-download snapshot type things to clients where they can then have each individual query be much cheaper. So you'll compute a superposition over your whole database for each epoch. And so using that computed sort of set of parameters, clients can generate individually cheaper queries, but they'll need to get that sort of superposition each time you update, versus you do everything as a stateless thing per query, where your individual queries are a little bit more expensive, but an update is also very cheap. Next week, we're running a workshop at PETS. PETS is the Private Enhancing Technologies Symposium, which is in Bristol. It runs yearly. And so we've got a workshop in PIR that will run on the first day of that next week. There's a nice schedule of sort of this year's academic groups. We've got, I think, 10 different papers that are works in progress or enhancing where PIR is. And this is within sort of a broader anonymity.gov project that I'm helping with that is looking at how we take privacy-enhancing technologies from academia into actual industry. So this pipeline of getting privacy and metadata private communication to scale with our communication. And that's been a couple years. We got some initial money from Protocol Labs, where the thought is if we're going to be actually storing anything sensitive or personal on things that are distributed, we need to be able to do that privately. And that technology is not growing as quickly as our AI and data analysis capabilities, which is a little scary. So we'll see how that goes. I think I'm most hopeful by the relatively fast progression and asymptotes of the work around FHE. That is giving us some orders of magnitude as they say now, and also the data construction. So that's why that's the.
What was the last thing you said? Construction?
This private information retrieval as an application of FHE. So as we get the ASICs to come online and tune FHE circuits, I think there's a good chance that we get a few orders of magnitude additional increase of the database problem. And it's a construction that is reasonably accessible to a lot of developers, right? You've got a very easy to reason about key value store abstraction that you can drop in, which means that hopefully that gets picked up.
What's your sense of what the pressures are for, like, I have a sense for example, why signatures might find their way in responses.
Yep.
Online for these kinds of technologies? Like, do you have a sense for what kinds of pressures might push companies to be more interested?
Data liability is probably one of the big ones, so regulatory such, you know, needing to police or having, I don't know, these strong regulatory requirements about policing content is increasingly making companies not want to know what the content is, because then they don't have to do that. They've got a stronger answer for saying, oh, I can't block the content that's mentioning this political group or whatever because I can't see the content. I don't know who's doing that. I can't give you, you know, the log of when they connected to me because I can't say who is accessing, you know, this copyright movie because I can't see what items people are accessing. So there's a set of liability reasons and regulatory reasons that I think align in particular with Web3 stuff, but more generally are causing people to, for the same reason that Signal is saying, look, we're end-to-end encrypting, we've got very few logs. Like if you get a phone number, we can probably eventually get you the IP address, but we're not able to give you the communications. It was that regulatory thing along with the PR that causes a lot of companies to go end-to-end encryption in response. And so you're going to see that continued game or adversarial game.
So, I'm just trying to understand this conception.
Yep.
As you mentioned, remind me of who even chooses that. This is from my memory.
Sure.
So, nodes for sources of data or particular information. And entities that are grabbing.
Mm-hmm.
But it's something like that.
You can tell who's grabbing.
And so, yeah. So is this taking account of just one-to-one?
So this is putting a server in between and delinking by making it so that you can't tell which item. So you would paddle your items to the same. I would publish some item, and now the client gets it. But you can't tell if the item the client gets is the one that I put. If there's timing things, you now need to worry about those again. But this is that same intermediary that you would get from a mixnet or something like that, that you've got some network process that's giving you a larger set that you can't distinguish from.
This is still given at the centralized. Because if you know,
Right. So this is, yeah,
because if you distribute that and you kind of know where
it came from.
then you can just look at where or deduce what it might have, what data it might have retrieved, or who might have retrieved.
You can get the full set of clients. So you can get the users, and you can get when the users are active and things like that. So this isn't your full solution, but this is one of the building blocks that gets you closer to an enemy. So there's a set of there's schemes for how you would do like a chat or communication built on top of this. This probably, like PIR fits with like ORAM or some of these things where you've got, which is oblivious access to a database essentially, which is like, I've got some set, I want to be able to access it without revealing you know, what's actually getting of interest. So ORAM gets used for like T storage. So if you've got your SGX and you're writing 1 byte, and you keep updating the one counter to go up, then even if your memory is encrypted, someone who's outside of your secure enclave could be looking in and being like, okay, whenever this 1 byte is changing, I can't see what the value is, but I can just sort of track how fast you're upgrading your counter. You don't want that. You want the accesses to sort of all be at random places, and so you need to randomize into that larger set. So ORAM lets you say, I've got my storage, but I want my access patterns against the storage to appear oblivious, so not matching what's the actual, oh, that is all the same thing, but I'm going to update random buckets and have sort of this tree structure to hide what's actually being done. This is a similar primitive. You've got a set of messages, and you want to be able to delink which items are being accessed, but you're not hiding group membership that, yeah, there's some client who is accessing this system overall.
We're out of time, unfortunately.
Great.
Thank you so much, Will.
Yeah.
So we have talks from Hirsch and
Mike.
There you go. About
ZKTLS.
ZKTLS, there you go. Thank you so much.